Welcome to another session on image enhancement. In the previous session, we had looked into some of the basic gray level transformations. In this session, we will be looking into the histogram processing. What is basically a histogram? It represents the number of pixels. It's a plot of the number of pixels having the particular intensity. Okay, where nk represents the number of pixels having the intensity Rk. That is the kth intensity level. Since this nk is the total number of pixels with kth intensity, then we can represent it as a random variable and we can associate with the probability. So nk is the number of pixels having the intensity of the kth intensity, and mn is the total number of rows and columns. So therefore, this gives us the probability of that intensity value. So the histogram looks more like the graph that you can obtain by plotting the probability. So if you take the image, this is a dark image. You plot the intensity, the number of pixels having the different intensities. So you will get a graph like this. Second, this is the image made little bright, and this is the lighter version of this, and this is the when the intensity is proper. So this is the proper one. Now if you observe here in this darker image, the information or the histogram is concentrated at the lower intensity values itself. Here it is concentrated in the middle region. Here, since since it is bright, so it is gone, his intensity is gone to the brightest points, and here it is having a proper intensity. So therefore this is more appealing for the viewing. So therefore this is having a proper intent. If you can see the histogram of this image, it is in a better way. So therefore we can understand from looking at the histogram, we can understand these points. If it is a dark image, it will have the histogram points or the plot lying towards the lower intensity region, and if it is the brightest one, it will be having towards the highest. And for not a blur image, it will have a very narrow histogram, and if it's a good image, very presentable, then it will have a wide histogram. So this is what is the information that we can obtain by looking at the histogram. The histogram, as we have just seen, reveals information about the contrast of the image and the mean gray level, but it has some problem. It doesn't give any information regarding the location or the type of objects present in it. And if two images have the identical histogram, but still they can be different in terms of what is present or what is contained in the image. For example, if you look at this image A and B, they both have this same histogram plot, but if you look at the content or what is present in image A and what is present in image B, both are different. So we cannot tell what is the content based on the histogram. So that will be the problem when you're using only histogram for processing application. Okay, next, let us define the histogram processing for intensity transformation. So it is still a point transformation equation we are using. R is the input, S is the output, and T is the transformation operation. So when R, the input takes the value between 0 and L minus 1, where 0 represents the brightest point and L represents the L0 represents the darkest point and L minus 1 represents the brightest point. So this is the transformation. Output will get a corresponding value. The condition for this is that the TR is a single value and it should be monotonically increasing. So what does this imply is that the output will never be less than the input. So that is the implication of this first condition. When we say that it is monotonically increasing, that means the function should not decrease and it should be a single value. Second condition for this transformation is that the intensity should be within this range 0 to L minus 1. So this condition implies that the output intensities will be same as the input intensities. When you take the inverse of this transformation, the output, the output value S should also be lying between the range 0 and L minus 1. So this implies that there is a one-to-one mapping between the input and the output. So if you look at this input-output relationship here, so here you see that multiple values are mapped into a single value SQ. So, but here there is one-to-one mapping. So what is monotonic is, this is also monotonic. That means it does not have any fluctuations. It is monotonous. So that is what is, it does not come down and go up, and that is what is monotonous. It is having a one, and it is increasing, monotonically increasing. So this is increasing. Now, what is the drawback of this type of mapping? Here we cannot perform the inverse because many of this intensities are grouped into one intensity. So when we're trying to inverse map it, we will have a difficulty in doing it. Whereas here we can perform the inverse mapping very easily. So that is the information that we can get by using this transformation image, the histogram processing. So what we desire is to perform the histogram equalization. What does that mean? Means that if you take the PDF of any arbitrary function and plot the graph and apply this transformation, it should give a uniform amplitude like this. The probability of that output should be an uniform function like this. So this is why, or it says that it is equalized. So that is why you get this name called histogram equalization. But since we are dealing with the image and it is discrete in value, so therefore we will not be using this PDF here. So how we perform histogram equalization? So we use this equation here. So the discrete input intensity Rk is mapped to a new discrete intensity Sk using this equation. Sk is equal to T of Rk. It's the same equation what we have defined previously, and but here we are just telling it in a different way. So L, so this is equal to L minus 1 into sigma k, sigma j is equal to 0 to k PR Rj. And this is nothing but Nj, that is the number of occurrences or number of the number favorable for this particular intensity. So that is what we are telling here, or the frequency of that intensity. And Mn is the total number of pixels. So the new histogram will be stretched or extended than the original histogram. That is what we can observe by the results. So the new intensity will be more, will always reach white since we are using this condition. So the resultant will be enhanced image, and there will be an increase in the dynamic range of the pixel values. So if you observe the image here, this is before equalization. You can see that the intensities is much less than 200, but here after equalization, you see the graph, it is increased in the or in the vertical direction, and the intensities are also increased in the horizontal direction up to 250. So this we call it as a histogram equalization operation. Now let us look at the same previous image. So these are the four different images: the dark image, the bright image, the dull image, and the correct image. So these are the images obtained by performing histogram equalization, and these are their corresponding histograms. And as I said, when the histogram is having, if it is concentrated on in the lower intensity region, that means it is very dark. If it is in the higher intensity region, then it is very bright. If it is in the middle and having a very narrow plot, then that means it is not a very good one. Next, if it is spread like this, then we call it as a histogram. It is a good one. It is more pleasing to the eye. So histogram equalization just performs that kind of operation where it is more, whatever be the kind of image present here, it is enhanced by performing histogram equalization. So another example, mathematically, let us look at this, how we can compute this histogram equalization. If you consider an image of 64 by 64 and 3 bits are used to represent that with 8 intensities, that is 0 to 7. So 0 to 7 counts 8 different intensities. So therefore, we'll be using 3 bits to represent that. So if Rk represents the different intensities 0 to 7, and Nk represents the number of pixels that are number of pixels that are having those intensity values, and this is the probability of this. So by calculating Nk by mm, we obtain this probability. So this in the problem, if they ask, these two should be given, or at least this should be given, saying what will be the different intensity values, so that we can go ahead for computation. Next, we perform the discrete histogram equalization. We calculate by using this formula. So we calculate S0, S1, and so on by using this formula, and this is what is shown here. So we get the corresponding S0 is 1.33, S1 is 3.08, and so on. Now after obtaining this value, next we round off this to the nearest integer. So 1.33 is rounded off to 1, and anything more than 0.5 is rounded to the next higher integer, and lower than that it is rounded off to the lower integer. So 3.08 is 3, 4.55 is rounded off to 5, and so on. So this is the value we had calculated. This is the rounded off value. Next, we are now going to map to the new variable. So P of 0 represents what is the output value being, intensity value being 0. There are nothing there. So it is output is having 1 pixel, I mean the intensity value 1 or 3 or 5 or 6 or 7, no other value. So therefore, the intensity for 0, 2, and 4 will be 0. The probability of the output having intensity 0 mapped to 0 or 2 or 4 will be 0. That is what we can see from here. Then probability of the intensity value mapped to 1 is same as the probability whatever we computed for input and output. So this will be same. So this will be equal to 0.19 as we can see from this graph, I mean the table here. Similarly, for P3, it is P of S1, which is same as P of R1, and P of R1 is 0.25. So, but P of 5 is P of S2, and P of 6 is P of S3 plus P of S4, because two are having these values. That means S3 also is having 6 and S4 is also rounded to 6. So therefore you have to add those two probabilities. So if you add those two probabilities, that is R3 and R4 probability, R3 and R4 probability, 0.16 plus zero point 0.8, 0.08 is 0.24, and so on. So P7 is 1. So like this, we get the new variable. Next, this is how we are plotting the original histogram, and this is the transformation function, which is shown as a cumulative, and here is the equalized histogram. So this is now you can observe that what is concentrated at this point is now spread out. So therefore we see that the histogram equalization is performed. Of course it should be uniform, but then you don't get a flat top. It is somewhat like a flat, because this is a discrete. If you are using a continuous function, then you will get a exact flat top that I had actually shown in the beginning. Next, when does this equalization not applicable? So whenever there are very narrow, the histogram is having a very narrow region, then it will produce, when you perform histogram equalization, it will produce false edges and false regions, and this can also increase the graininess and patchiness. What is that? We will see now. For example, if this is the image we are obtained, and this is the actual image and its corresponding histogram. If we perform the equalization for this, and this is the equalization, and we see that there is graininess, a lot of grainy and patchy appearance. So this is, and whatever is a shade, it gets attached to the coin. So that is called the false edges. So a lot of these problems that you can observe when you do the histogram equalization. So histogram equalization cannot be applied for all cases. When, especially here, we see that the histogram is very narrow in this region. For such a problem, we should not go for histogram equalization. Next, this is another example, is the phobos, or the moon from the Mars. So when we take the perform the histogram equalization, we see that it is worse than the actual image. This is the actual image, the histogram of this, and this is the transformation function, and this is the histogram of the equalized image. This is the equalized image, so it appears more blur and it is not proper. As I said, histogram will always try to push the in all the values towards the brighter region. So this is what has happened. So this lower region is pushed into the brighter region. The histogram matching, we can overcome this by having the predefined or pre-specified histogram. So this type of histogram processing is called as histogram matching. So in histogram matching, we should have some specification of what histogram we actually want, and we try to map to that. So here we represent it as z is equal to t of r. So we, for the specific PDF, that is a probability density function, pz of z. So the histogram specification uses the histogram equalization as an intermediate step. So we still use histogram equalization, but not as a complete step in histogram matching. So what we do is, in the histogram matching, here this is the first step where we initialize the histogram, equalize the histogram of the image. Next, we equalize the histogram of the target by using this equation, and then we try to do the inverse transform mapping. Now, as considered for the same previous example, now this is the original histogram we got, and we have seen what is the modified uh, histogram we had got for the equalized for the histogram equalize. I mean, what we performed in the previous case. Okay, histogram equalization. Now, this is the histogram matching. So we want the histogram to be of this pattern. So let us see how we are going to achieve this. So this is the result to obtain from the previous problem. And this is where we stopped with the previous problem. Now let us take this further. So as I said, this histogram equalization is the basics for histogram matching. So we have performed histogram equalization and obtained these results. Next, uh, so this is the desired intensity from the, uh, this is the desired intensity 0 to 7, but and having the probabilities from the desired, we observe the probability. For 0, there is nothing. For 1 intensity, there is nothing. For 2, nothing. For 3, it is having 0.15. And for 4, intensity value 4, it is having 0.2 and so on. So we find the probability from this, and therefore we have got the desired intensities and its probability. Next, we find the cumulative distribution by adding one one by one, and then we multiply by 7, which is the largest intensity value. So we multiply and convert it. Next, we round this to the next, we perform rounding operation. So 1.05 is converted to 1, 2.45 is 2, and this is 5, and this is 6 and 7. So we have got the normalized values for the new desired intensity. Next, in the next step, so we have these two now. So this is the desired intensity and this is the normalized intensity. So how we perform the new variable is that, so we see that this is what we have obtained from the previous, that is the equalization, histogram equalization. We have obtained this result, and this is what is the result we have obtained from the desired, right? So we have to map this. So 1 is present here and its corresponding intensity is 3. So we write 3 for that. And here 3 is here. There is nothing 3. The nearest is 2. So the corresponding for that intensity is 4. So we put 4 there. And 5 has the same in here also. And it is the desired also is 5. So we put 5 for that. 6 and 6 are mapped to 6. So we have 6. All these are mapped to 7, which is having corresponding value 7. So all these are having 7. So therefore, this will be the values. Now for 3, we have the value of 6, and this will be the probability. So this will be the final histogram. Thereby, we see that the histogram matching has happened, and it's not exactly the same as what is indicated by the problem, but it is a better version of the, better than compared to the histogram equalization. So this is histogram matching. Now let us look at the same Phobos moon plotting. So this is the histogram matching. This is the specification or the specified histogram, the constraint, and uh, this is the transformation. So this is the enhanced image by using this curve here. So this is the obtained by doing the transformation, and this is the histogram of this image. So we see that the image is better than what we got by using histogram equalization. Now both these are global operation where we are not confining to a region. So this is for the entire image we are performing. Next, we can have the local enhancement also. Why we should go for this local enhancement is we can use it for pattern detection, and we can use it for adaptive enhancement, and for adaptive thresholding, and even for object tracking that is based on histogram. You can use this. So what are the steps involved in this local histogram processing? First, we define a neighborhood and move its center from pixel to pixel, find the local parameters there, and then apply the histogram equalization or matching at that center and process that image. So by doing this, the overlapping computation is this non-overlapping computation is fast, but it is blocky and it has different contrast level for each individual region, and therefore it requires post processing to remove this blocking artifact. We will see this here. Yeah. So this is the uh, window size of 25 by 25, and this is by using 64 by 64, 100 by 100, and 200 by 200, where the picture is more clear. This is local enhancement. So you take a local pixel size of 25 by 25 and then find the equalization, perform equalization and matching and do it. So this is the result obtained. You can also use the statistics of the image, that is the local mean and variance. So if you do the local mean and variance, this is the image, this is the resultant you get. This is the actual image of the failed tungsten filament, and this is the result of global histogram equalization, and this is by local histogram statistics, using the local histogram statistics. What are the statistics? Mean and variance. So you can use that and process this image. So in this discussion, we had looked into the histogram processing. So far, we have seen the basic gray level transformation, the piecewise linear transformation, and histogram processing under this image enhancement. These are all the spatial domain techniques. Now, next we will be looking into another spatial domain operation, that is the spatial filtering. Thank you.